Space, the final frontier. This is the Observer's Notebook, the official podcast of the Association of Lunar and Planetary Observers. Its mission to explore the solar system, to seek out new observations and data, to boldly go where no podcast has gone before. And now the host of the Observer's Notebook, Tim Robertson.
Hello and welcome to episode 87 of the Observer's Notebook, the official podcast of the Association of Lunar and Planetary Observers. My name's Tim Robertson. I'm the host of the Observer's Notebook and also the coordinator of the training program with the ALPO. Hey, thanks for downloading and listening. The Association of Lunar and Planetary Observers collects and analyzes observations of various solar system bodies and associated phenomenon, and publishes these in detailed reports concerning these bodies in its quarterly publication, the Journal of the Association of Lunar and Planetary Observers. This podcast depends upon donations from you, our listeners, to keep it alive. If you do enjoy what you hear on the podcast, you can donate to it via Patreon. You can give as little as $1 a month. If you feel even more generous, $5, you receive early access to the podcast before it goes public. For a monthly donation of $10, you receive a copy of the Novice Observer's Handbook, the official handbook of the training program within the ALPO. And for $35 a month, you receive producer credits on the podcast. You can help us out by going to patreon.com, that's patreon.com/Observer's Notebook. If you'd like to join the ALPO, membership begins at only $18 a year. For more information, you can find us on alpo-astronomy.org. And we are also on the Facebook. Just search for ALPO Astronomy. And this podcast also has a Facebook page as well. Just search for Observer's Notebook. And if you enjoy what you hear in the podcast, please subscribe. That way you'll never miss another episode of the Observer's Notebook. And now, episode 87, a very special one. I think you'll enjoy it. All right, I'd like to welcome everybody back to the Observer's Notebook podcast. Today we have a special guest from Software Bisq, the senior software engineer and product developer, Richard Wright. Welcome to the podcast.
Thank you. Thank you very much for having me.
Now, before we get into our topic today, why don't you just give everybody a little bit of introduction about yourself, what you do, and things like that.
So I work for Software Bisq. I'm one of the senior developers there and imaging specialists. My specialty coming into Software Bisq was cross-platform and graphics technologies. And actually, when I joined the company about 17 years ago now, I really wasn't much of an imager, or I was a closet imager. And I got more involved in imaging not long after I started working there, and I started working on camera plugins for the sky. And so that developed kind of a love for camera technologies, and so I sort of just specialized in that to some degree. I've been an amateur astronomer, I guess, since childhood. Mostly visual, up until about the last 20 years or so. Got into imaging.
Okay.
But my primary profession is software developer, software engineer. So I'm kind of an accidental astronomer. One of the great things about being a software engineer is every discipline, every industry needs computer people, and I just really loved astronomy. And it was like, well, shoot, somebody in the astronomy field needs a programmer. So
there you go, marry the two together.
Right. So I was not happy where I was, and so I started looking around. And actually, I worked for Starry Night initially, helping them with their OpenGL implementation, and then left them about a year later and joined Software Bisq, and I've been with Software Bisq ever since.
Great. Now you're in Florida?
Yes. I get to work remotely from Central Florida. I live kind of outside Orlando.
Okay.
Skies aren't too bad here. I'm not like on the side of Orlando where all the attractions are. So I can do narrowband stuff, and I can do a lot of research and development in my own backyard. But I have a dark sky camp down in Okeechobee, Florida, which is right next to a big state park and a lot of dairy farms and sod farms. So you can see the Milky Way down there, and I can get in some dark sky imaging from there.
What type of observing equipment do you have?
all of it.
That's a typical answer when I ask that question. That could be half the podcast, just naming off telescopes.
Right. One of the best things about working into the industry is, it's all, some of it is, I have 3 Paramounts, out of the Mighty and the Index Plus and the Paramount Indy. I call that the company cars. And I have a lot of cameras because I do support for the cameras. So I kind of figured that out, pretty early. It was like, nobody really wanted to write camera plugins. It was like, well, I'll do one. Well, that wasn't so bad. And, I get to play with the camera. And then it was like, well, I'll do another one. Yeah. And next thing you know, I have, a nice arsenal of cameras. I have the world's best mount and the world's best software. And telescope-wise, I've kind of had to accumulate those on my own. But I have I've procured I've got a nice collection of refractors. I have all 4 of the Esprit Skywatcher refractors. And I have a Lomo Russian refractor and a Takahashi, and I've got the Riccardi Honder's RH200, so the Veloce from Officina Stellare. That was my first big telescope expense. I think it was the most money I'd ever spent on anything other than a car, and I kind of had to sweet talk my wife a little bit. We had a little bit of a financial windfall, and I said, you know what I want to do with this? I want to buy a really expensive telescope. And somehow she was like, okay, whatever. And that was sort of the beginning.
You found a good woman there.
Of my collection.
That's good. Now, can you give us a little bit of background on the history of Software Bisque?
Software Bisque has been going since 1984. Our founder, Steve Bisque, was in a bike accident and laid up and said, bring me my laptop. I can't lay here and do nothing. And so he started making an astronomy program, and he called it The Sky. And a couple of years later, he was advertising it in Sky and Telescope. And a couple of years later, he was hiring his brothers. And a couple of years later, the rest is history, so to speak. So it started off just software with The Sky, and then they got into making mounts and camera control. They partnered with SBIG early on, and some other people. They really pioneered a lot of what we take for granted today in terms of a computer program on your laptop controlling your mount and controlling your camera and using a guider and all that sort of thing. And so it's been about over 30 plus years. I think it's close to 35 years now that they just celebrated them.
Yeah, I think I had maybe version 3 of The Sky. I don't know. It was an early on version years and years ago.
Right.
Wow. Great. Yeah. Well, I reached out to you a little while ago because of an article that you wrote in Sky and Telescope magazine, and it was titled CCD, CMOS, and the Future of Astrophotography. And that just jumped out and grabbed me. I want to know what the future of this is, because this is a big deal to us amateur astronomers. What is the next best thing? What's going on? What's going to, what kind of imaging are we going to be able to do next? So if you can, in a nutshell, can you give us just a brief history of imaging?
A brief history of imaging. Let's see. In the beginning, there was film, and I did some film imaging, but I was a complete and total coward. I imaged the moon with film.
Okay.
So with a big reflector, you can shoot the moon just like you can shoot birds. It was no big deal. 1/800th of a second. You bracket your exposures and you bracket your focus. And I took the film to Walmart and had them develop it. So yes, I did astrophotography with film, but it doesn't really count. If you talk to any of the old timers who had to do film hypering and guiding through the eyepiece, out in the cold, those people were those are the real heroes of imaging. Right. I think if I had been imaging electronically, I'm pretty sure I would have beat SBIG to inventing the auto guider, because there's no way I would have sat out in the cold with a joystick and tried to keep a star centered on the crosshairs.
Oh yeah, I know like Tony Hallis and Bob Farr and people like that, and I knew them back in the 80s when they would do these 6-hour exposures all night, and then an airplane would fly across the field of view, and I'm like, oh god, guys.
Those people are athletes. That's an endurance sport.
It really is.
To do that, really. Yeah,
it really is.
Yeah. CCD imaging came along. The CCD chip was originally not even envisioned as an imaging chip. It was originally designed to be a memory circuit, and it turns out it was. I'm not sure the story how they figured out it was sensitive to light. Light would dislodge some electrons, and it would build up in the wells, and then you could read it out, and you would get numbers for each pixel, and those numbers indicated the brightness of the image. And so first, they were all monochrome, and we would put a red filter to get red light and a blue filter to get blue light. And later on, somebody named Bayer came up with an idea of putting down a Bayer matrix on the monochrome chip. Mm-hmm. And that covers some of it. Really, color chips and monochrome chips are the same chip circuitry. Just one has a layer of colored filter on top of it. So you get a red pixel and a blue pixel and 2 green pixels. And so you get sort of this screen door pattern image, and it just sort of you interpolate the values to make the color image. And, you don't get as much data when you do that. Those filters don't block a lot more light than the monochrome filters do. So the efficiency of the chip isn't quite as high. And you use a little bit of spatial resolution. But, in the long, look at a DSLR, nobody who shoots with an electronic DSLR is complaining about those issues. So I think that if we worry about that with faster photography, it's sort of a fringe case. If you have fast optics that deliver a lot of light to a color sensor, you're going to get plenty of signal, and you can make do with that. Of course, monochrome is a little more flexible if you want to do narrow band or some fancy stuff. I like to do infrared sometimes, or just shooting hydrogen alpha. I also think people should shoot luminance. It's surprising what you can get from luminance, even under a light polluted sky.
What you said, luminance?
Yeah, luminance. Just shoot black and white. Like really shoot black and white. Don't try to make a color image. And I'll get some hate mail about this, but color imaging is hard. It's so much easier to learn to stretch and calibrate with one color channel. And most color images, when you first start, they look terrible. Learning how to color balance is a tricky, right, difficult thing. And beginners want to see something in color, but I think beginners would be a lot more successful if they started in monochrome and made beautiful monochrome images. So I like to just shoot monochrome sometimes. You get so much more contrast from them, especially if you're under light polluted skies, or even you could shoot hydrogen alpha for that. But anyway, that's an editorial you probably weren't looking for.
No, that's fine. It's fine. It's interesting. Now, in your article, you say that the days of CCDs are numbered. Why?
Well, the days on any technology are numbered. They're going to be replaced by CMOS, most certainly. It's a question of how many. Is it a big number or is it a very small number? Really, anybody who's shopping for a camera shouldn't look at, oh, that's CMOS, I should get it, or oh, that's CCD, I should not get it. By and large, the gap between the two are closing. I guess sort of a summary, and you can drill down on this. I suppose the summary is CCDs still work better for low light imaging. They calibrate better. They have less. A lot of factors that really make them well suited for that. CMOS is catching up very quickly. The catching up doesn't mean it's caught it. It just means that it's getting closer. For some applications, CMOS is really kind of already won. Like for lucky imaging, if you're doing solar system, lunar or planetary or solar imaging, and you're trying to do video, by and large, there are some very, very fast CCD chips, but they're horribly expensive and they're very niche. But by and large, you can get a cheap CMOS camera that can do 60 frames a second, and CCDs really can't compete with that. There are some noise characteristics and things that people want to argue about, but when you're shooting the moon or Jupiter with a 14-inch telescope, you've got a lot of light. And so some of the things we worry about for deep sky images don't really count,
right,
in those situations. So I would say that in the realm of lucky imaging and solar system imaging, CCDs have already surpassed. CMOS has already surpassed CCD in terms of value.
Yeah,
and what they can do.
This article grabbed me partially because of what I do for a living. I work for NASA and on a Earth weather satellite. And one of the instruments I work on is called VIIRS, Visible Infrared Imager and Radiometer Suite. And one of the big detectors we have on it is a day-night band. And so with this, we use CCD imagers, and just like you said, they're really sensitive to low light. And some of the prettiest pictures we have from our satellite are the nighttime images of the Earth.
Wow.
So that's and I talked to actually one of our scientists about this. I said, "Are we going to go CMOS?" He goes, "No, right now CCDs are the way we're going with our instruments." So it's interesting. Now,
right. I think that in the amateur community, it's hard to convince people that they should stick with CMOS, or that CCD is better. Scientists that I talk to, I've talked to some scientists, and CMOS just isn't anywhere close. One of the problems is amp glow. It really throws off calibrations, and they're doing some very meticulous calibration. They need things to be very accurate for photometry, and you can do a lot of useful things with CMOS today. But one that I was talking to, he said there's nobody has a CMOS camera, because if they did, they'd buy it. That will do as well as what they want to do. Now that doesn't mean that's not going to change in the near future. Already there's new CMOS technologies on the market. There was a paper I read a couple of months ago in a physics journal on how to fix amp glow in CMOS sensors. I know Starlight, I know at least one other vendor that's working on a low amp glow technologies. And there's some other things. CMOS, some of the pattern noise on CMOS is also worse than on most CCDs. And the thing is, you remember comparing CCDs and CMOS is like comparing hamburger and steak. I think I mentioned this analogy in the article, but I'll say it here too. In general, you can say steak is better than hamburgers, but it depends on where you're getting the hamburger or the steak, and it depends on how hungry you are, and it depends on what your thing is. There's people listening to this right now saying, well, I did this with CCD and I did this with the CMOS, and the CMOS was better. And I have no doubt at all you can find a CMOS sensor that beats a CCD sensor. So we're being very general here, because, a cheap camera is going to perform like a cheap camera. It's not going to matter whether it's CMOS or CCD. And a really expensive camera is going to work really well. Usually, it doesn't matter if it's CMOS or CCD. There's some very good CMOS cameras on the market. I'm pretty particular as an imager, and I have my favorite CCD cameras that I just love. And for a long time, there was no CMOS camera that I liked. Friends would get them and they would show me their images, and it's great you can get an image, but I know that you had to work really hard to get that image in post processing, because I know that they don't calibrate very well. But that was a couple of years ago, and currently I have at least one CMOS camera that I've used a couple of times. It's full frame CMOS. It's made with a DSLR chip. It's an expensive CMOS camera. Nobody's $500 camera is going to beat a $3,000 camera. But if you this particular CMOS camera that I'm talking about, it's about a $3,500 CMOS camera, and it does very well. It's not very noisy. The pattern noise is extremely low, so it calibrates out well, or you just expose long enough to get over the pattern noise, and it does a very good job for it. I'm very excited. I haven't had a chance to try QHY 600. Everybody is raving about that. That's a monochrome CMOS, and it's a 16-bit readout. A lot of people don't realize how important it is to have more than like a 12-bit readout on your camera, but a full 16-bit readout with deep wells on a CMOS chip is quite remarkable. And 5 years ago, you couldn't find a chip like that available to amateur astronomers, and you can today. So imagine, in another 5 years, what's going to be out.
Yeah. Now I'd like to back up
sure.
a little bit.
I just kind of blather a lot.
No, this is fine. This is fine. I want to appeal to all of our listeners out there, and I'm sure there are some that are going CCD, CMOS. I don't know what the heck you're talking about. So can you just give us, explain the architecture of CCD versus CMOS imagers and what the differences are?
Sure. So a CCD, how any imager works is they're made out of silicon crystals. And when light hits those crystals, and I'm being very overly simplistic here, but when light hits those crystals, it dislodges an electron, which is a subatomic, atomic particle, an electron. And the sensors have sort of buckets that collect these electrons. So as light hits the sensor, each photon can turn into an electron, and then you can read out and see how many electrons there were. So if you read out 500 electrons, that means you detected 500 photons of light. Now, not every photon gets converted into an electron. We call that the quantum efficiency. So if half of the light turns into electrons, we call that a 50% quantum efficiency. And in that regard, both CCD and CMOS really work the same. They work by the same physical principle that turns light into an electron. It doesn't really turn it into an electron, but that counts light with electrons. The big difference between a CCD and a CMOS is the CCD is laid out in a grid pattern, and the buckets of electrons with the numbers in it get shifted, sort of like you've seen an old movie where there's a barn on fire and you get a big line of people with buckets and they're passing the buckets left and right. That's sort of how a CCD reads out the image. It reads out one pixel at a time, one row at a time, and it just kind of shifts all of that data. A CMOS sensor, instead of shifting the data out like that, it actually reads out all of the data sort of simultaneously. Yeah. And so this is really the biggest advantage of a CMOS sensor is the readout speed. It can read all of those pixels into memory very, very fast, where the LCD has to shift all of those pixels to come into memory. The cost of that is CMOS sensors are far more complicated. There's actually quite a bit more electronic circuitry on a CMOS sensor than there is on a CCD sensor. Also, all of that electronics adds, different challenges to the chip. If it's not, the electronics get in the way of light getting to where it can be detected. So sometimes the quantum efficiency can be a little lower for a CMOS. I would say that problem's been largely solved, but it's a challenge due to the technology. Also, all of those electronics add additional noise. So when you're reading out the data, it's not perfect. And so the data fluctuates a little bit. We call that the read noise. In addition to the read noise, all of that extra circuitry is energized and it emits infrared light or heat. And that also creates false signal in the CMOS chips. And so now you've got amp glow and things in the corner. And sometimes that is not, it doesn't calibrate out very well, meaning if you take a dark frame that's got the amp glow and you take a light frame that's got the amp glow and you're like, well, I'll just subtract the two and it's on. But it's not that repeatable, so it doesn't really clean up the amp glow that well. Plus the amp glow is building up signal, which is filling your buckets up. And so now, if you've got a lot of signal from your deep sky object, you've got the amp glow adding to that, and you can kind of run out of a little bit of room in those areas. So those areas with severe amp glow don't clean up very good. And that's also, the amp glow has gotten better just in the last few years. And I think it's a problem that'll go away completely. And, certainly within, the next decade, probably sooner than that. But it's still an issue, and it's still a competitive advantage that CCDs have over CMOS sensors right now.
Interesting. Yeah. 10 years ago, professional photographers, if they used digital SLR, they all had were they still using CCDs about 10 years ago, weren't they?
Right.
Yeah.
And now they're CMOS.
CMOS.
That's another important factor. about CMOS. People who've been making CCD cameras for a long time have a lot of experience. And you'll see a DSLR can use a CMOS chip and you get a pretty clean image. If you buy a low cost CMOS camera, it can be pretty noisy. One of the reasons for that is that the chip manufacturers, when they sell chips, they also provide kind of what we call a sample implementation. They'll provide a camera kit. Here's a sample electronic design for a camera to control the chip. And so a budget camera, they'll just use that sample design around that chip, but the sample design is not very good. If you've got somebody like Canon or Nikon, they've got engineers who are, very highly paid engineers who are very good at what they're doing, and they'll design those cameras and they'll get very good data out of the CMOS. If you're using one of those camera kits, it's almost like a build-it-yourself radio shot kit. You're not going to get great results. But again, at the same time, this was true 5 years ago. Most CMOS cameras, in my opinion, were very poor. But the CMOS camera vendors, they've had 5 years of practice. And so they're starting to modify those designs and they're starting to learn some tricks. And the CMOS cameras are, again, they're getting very good. I don't know if I just kind of want to reemphasize the point. A friend of mine the other day said he said, "Hey, I was looking at this camera at CMOS. What do you think?" And I'm like, "It's not one I would want, but I have a $10,000 CCD camera that's really great. If you can only afford a $1,500 CMOS camera, you're probably still going to get good results out of that. Right. It's not fair to say, well, if you can't afford a $10,000 or $5,000 CCD, I guess you shouldn't get into imaging at all." A lot of people are getting really great results with CMOS cameras. So again, I'm not saying CMOS isn't any good, but it's like comparing steak and hamburger. And I've had some really great hamburgers, and I've had some really lousy steaks. I'm sure everybody else has too. So okay.
Yeah, in your article, you discuss the challenges of CMOS, and you mentioned non-linearity and amplifier glow. What is that?
Well, the amp glow is what I was talking about a minute ago, where the circuitry on the CMOS chip is warm, and so it's heating up the chip, which creates a fake signal. So it's not really signal from your target; it's signal from the electronics that's polluting your image. And I saw amp glow. I had the original Canon Rebel. I remember when I bought that. And I bought it for regular daytime photos, and then I started using it for astrophotography, and it had pretty bad amp glow at the bottom. But I don't see hardly any amp glow in a modern DSLR, and so there's no reason to think that that's not going to happen with astro cameras as well. In fact, it's already happening with astro cameras. I've seen a lot of CMOS cameras that have almost no or negligible amp glow. I know for science, almost no amp glow isn't quite good enough, depending on the type of science you're doing. Right. Of course. Now the nonlinearity is also important. So linearity it's a little bit hard. It sounds like some kind of fancy math word or something. But really what it means is, if you get X amount of light, you get X amount of signal. And if you get 2X light, you get 2X signal. So you put 10 times more light in there, you get 10 times more signal. You put 1,000 times more light, you get 1,000 times more signal. So that's linearity. And CCDs are largely linear throughout most of their range. CMOS bounces around a little bit. So if you add twice as much light, you may only get 1.8 more signal. And then you add 4 times more light, and you get 3.9 times more signal. And so what that causes, one of the problems with that is if you're doing photometry, like you're trying to measure star brightness, if it's really severely nonlinear, then you can't use it for that type of science at all. If it's only a little nonlinear, you can get away with it. But the problem with nonlinearity too is if you're trying to calibrate your images with flats, it makes it very difficult to get good flat field calibrations. If you have a very clean imaging system and all you have is a little vignetting, you might can clean that up, with a post-processing tool that fixes the vignetting. But if you have dust bunnies or other types of optical aberrations, plus there's a type of noise that you get when with high signal data. So if you're under really light polluted skies, there's a type of noise called PRNU, or photo response non-uniformity. But it's a type of a granularity noise that only flats actually calibrate out. But if the sensor's not linear, that calibration again doesn't work.
Is that pattern noise?
Yes, it's a type of pattern noise. Yeah. Okay. Yeah. Every pixel is not 100% identically sensitive to light, and so there's some variation in the sensitivity of light from pixel to pixel. And that's what that represents.
And CMOS is more susceptible to pattern noise than CCDs are.
Well, CMOS has the same type of pattern noise as the PRNU. Without a linear response, it's very difficult to calibrate out the PRNU. Since you brought up pattern noise, there's also dark pattern noise, which is what the bias frames will calibrate out. And one of the problems with low-cost CMOS, and I don't see this as much in the more expensive CMOS cameras because it's due to the electronics around the chip, is the pattern noise moves around a lot. So if you do like picture after picture and you're like taking darks, or you're doing a high frame rate and you're looking at the bias, you see these lines bouncing all over the place. On a CCD, it's mostly static, bouncing all over the place. On a CMOS, there's lines and they bounce up and down, and they're never in the same place. And so those don't calibrate out very, very readily. And if you don't get a lot of signal in your deep sky imaging to get high enough above that, then when you start stretching your image, those lines and artifacts start to come out. And when you stack your data, sometimes you see streaks in it, and that's all from that pattern noise. And it's because it didn't calibrate out very well.
Now, look, for long exposure deep sky astrophotography, how do CCDs and CMOS imagers compare in the term of like dark current thermal noise?
The CMOS is, I think the CMOS is a little worse.
Okay.
So the CMOS is better for shorter exposures, whereas CCDs stand up to longer exposures a little bit better.
Is that because a CMOS is more sensitive, or?
The CMOS is, no, the CMOS has more, the amp glow gets worse the longer you expose, and the thermal noise is often worse, the longer you go.
Okay.
That makes sense?
Yeah.
Okay. Great.
Wow. Now, cost benefits, like you mentioned earlier, that it's an amateur astronomer. If they don't have an understanding wife, lets them go out and buy the most expensive telescopes that they've ever gotten. What are the costs? Is there a line in the sand that you would say you can get a good CCD imager up to this point, but after this dollar value, I'd start looking to CMOS? Is there something like that?
No, I don't really think so. I mean, if you have an unlimited budget, you're probably going to buy a high-end CCD camera.
Okay.
Most people don't have an unlimited budget. So if you only have $5,000, really $5,000 is going to buy you a really good camera, whether it's CMOS or CCD. I think people don't get into trouble until they're down in I only have $1,000 to spend. And then, realistically, even then, you're going to get a camera that's usable. And the only thing the only really thing that people need to understand is your $1,000 camera is not going to perform as well as a $3,000 or $5,000 camera. If you have a cheap CMOS, a cheap CCD camera, it probably isn't going to work as well as an expensive CMOS. And if you have a cheap CMOS, it's not going to work as well as an expensive CMOS.
But could you write some software to make it as good?
I've had some conversations about trying to make, basically sort of characterize your CMOS sensor to make it linear or seem like it's linear. I'm not sure that's going to be necessary in the long run. I think in the long run, they'll fix the linearity problem. But Yeah, I mean, it all boils down to image processing. What I love about a really clean CCD image is if it's well calibrated and well exposed, they're just very easy to process.
Right.
I don't have to do a great deal of noise control, and I have to do a lot of fancy algorithms to try to fix it. I don't want to spend 8 hours processing my image data.
Mm-hmm. True. Now, for planetary imaging as opposed to deep sky imaging, are there sensor preferences there?
For planetary, I would say for planetary, yes. To buy a really fast CCD camera is I'm talking to a friend who works in the semiconductor industry, and he was telling me there are CCD cameras that are just as fast as a CMOS camera, but they're not in our market. They're not in our domain. I have a $300 or $400 ZWO camera, and it does great. I do lunar, and I'm not singling out ZWO specifically. I'm just saying there's a budget camera, and it does a high frame rate, and you get a lot of signal from the moon or the planets. And I don't know that I could do better with a CCD camera than I could with that very low cost CMOS camera. You get a USB 3 connection because a lot of the noise problems when you've got a lot of signal, the other types of noise are much easier to mitigate. You're doing very short exposures. The signal is way above the pattern noise. And chief concern when you're trying to beat the seeing with Lucky Imaging is a high frame rate. So you just can't beat, a CMOS camera with a small chip on a CMOS camera for a high frame rate. And you got so much light coming from your solar system object,
right?
That a lot of the noise problems sort of fix themselves. You still need to calibrate your flats most likely, but the thermal noise and the dark pattern noise isn't as much of an issue when you're doing that short of an exposure with that much signal on the chip. Okay.
What about deep sky imaging?
For deep sky, I would say there are some CMOS chips on the market that do very well, and that do very well already. I have, like I said, I have one CMOS camera that I like to use from time to time. It's a one-shot color, and I don't always shoot one-shot color, but when I do, that's the one I use.
Okay.
But I've got a 16803 and a 16200. Those are pretty good sized mono chips, and I guess the 16200 is probably my favorite. Is one of my favorite sensors in terms of giving me a nice clean image on a big chip. The Sony 694 is also a miraculously clean and sensitive sensor. Its problem is it's very small. And those sensors are going to be around for a while. Sony's making those. You'll be able to buy 694s for another 10 years probably.
Oh, okay.
But it's a very small chip. So, we want bigger chips a lot of times so we get more real estate.
True.
Not everybody has a closet with 13 different telescopes where they can just pair it.
I don't know. Most of the people I talk to on this podcast do.
But it's great fun to pair a telescope with a camera like that. It's like pairing wine with meat or chicken or something.
Now you're talking
like,
my language.
I'm shooting in 41 tonight. Well, I think the 100 millimeter paired with the 694. I often will just kind of pair up the equipment based on what it is I want to image.
Okay.
Anyway.
Yeah. So is the imaging technology caught up to the optics, or is it the other way around?
Yeah, that's an interesting question. A lot of people, I don't know that I've met many people who realize that optics have gotten so much better in the last 10 years as well. 10 years ago, an f4 telescope would be, a marvel. Mm-hmm. And everybody's making f4 telescopes, or an f5 refractor.
Right.
And then look at the RASA, f2. Mm-hmm. So my Veloce was f3, and that was buying a Ferrari. I've had that. I don't know if I had that Veloce. It's been almost 10 years. But having an F3 telescope, when I bought that telescope from Officina Solare, that was like, I was a cool kid on the block with the Ferrari. But now everybody's got a telescope that's a lot faster.
Yeah.
And that makes a difference because you've got all that aperture and you're concentrating that light down to very small, and it means you can use smaller pixels. It means that you're not as much at a disadvantage if you're shooting one-shot color that you used to be. So it's really made a huge difference in helping us get better images. And of course, the electronics are getting better too. Probably one of the biggest things that has gone down is the read noise. Read noise being it's one source of noise that you really can't calibrate out. So you either need to take tens of thousands of images to stack out the read noise completely, or you just need to expose long enough to get your signal above the read noise. Well, when the read noise was 40 electrons, that means you had to get a really long exposure to get any data above that. Now your read noise is, 1, 2, 3, 4 electrons. And so you can get away with much shorter exposures in your stacking process.
Interesting. Now, where do you see the future of imaging? Do you see a chip out there in the future that is being developed or that you've heard about that might be something exciting for astronomers?
Well, I think the future is something I call, not me personally, something called computational photography, where we're going to start doing a lot more image processing on the fly while we're imaging. We're about there on sensors. I mean, there's two metrics on a sensor that really affect performance the most. One is the read noise, and the other is the quantum efficiency, or how efficient is it at converting light into signal. Well, we're already at 90% quantum efficiency with a lot of these back illuminating chips, and you can't get more than 100%. So we're almost as sensitive as we can be as far as detecting light. We're going to be limited by how much light is actually falling on it, not by the sensor itself. The other thing that affects that is the read noise, and the read noise is down to about 1 electron, and there's not much further down you can go. Effectively no read noise. We might could see that. It's still going to be 1 electron. It's still going to bounce around 1 electron. I think we'll have a hard time beating that. But, with almost no read noise and almost 100% quantum efficiency, we're limited by how much light is falling on our sensor. And scopes are getting faster. F2, F3, right. F4 is not uncommon at all. I mean, if you're on a very tight budget, you can get an F4 Newtonian and a coma corrector and get great results on a fairly speedy optical system. So yeah, what are we going to do? I think the low read noise is a key in the ability to sort of stack on the fly. Imagine you're taking much shorter exposures and you're evaluating each exposure as you pull it in. Sort of like Lucky Imaging on the moon. Like, what if you could evaluate those frames as they were coming in? Instead of having a 15 gigabyte file, you're throwing away bad images right on the fly as you're shooting. And now you got a much smaller file, a much smaller video file, and it's just the clean images. Or live stacking. Live stacking accumulates an awful lot of really short exposures. Well, right. There's ways around that too. You could live stack and then like save intermediate steps, and then later on you go back and you recombine the intermediate steps. I think how we image is going to change, and the techniques are going to change. The technology is changing. We're trying to use the old methods and trying to adapt the old methods to the new technology or the new and improved technology. Eventually, we're going to figure out maybe there's some better methods that we can use now that some of the hardware limitations are out of the way.
Interesting. You talk about live stacking, and I recently got the new iPhone 11, and it's got a live feature when you can take a photograph. And what it is, I think it's like a 1.5 second photo tiny, tiny movie that it takes. And then when you look at the photograph, it looks the best image. It already figures out which one's the best image, which one the person wasn't moving in, and that's the image it gives you. So it's basically, I think what you're talking about is live stacking.
Right. A lot of these techniques that we use in the astrophotography, we think we came up with it, but they actually came up with by other people doing machine vision and other types of imaging applications.
Well,
there's an Android app.
Like you said, the CCD chip was not for imaging.
Right. Well, yes.
Interesting. Wow, that's fascinating. Now, you've written a book on this, or?
Oh yeah, I wrote it's a tabletop book. It's called The Evening Show.
Okay.
Revealing the universe through astrophotography. It's not technical at all. I wrote it for my family and my neighbors and my friends. So it explains astrophotography like you were explaining it like I was explaining it to my daughter. So it's like, okay, so there's nightscapes. You put the camera on the tripod, and these are the types of pictures you get. And you get a telescope, and you do this, and these are the types of pictures you get. And, and I explain a little bit of astronomy. Somehow, if you go through the book, you just accidentally learn the difference between emission nebula and reflection nebula and galaxies and some of the techniques. So, it's on Amazon. You can get a print copy or get it on Kindle or a book.
I'll look it up and I'll put a link for it in the show notes so people can just go it and hopefully sell some books for you. Sure.
Cool.
You have anything else you'd like to add on the subject or on your article?
Let's see. Another factor, I don't know, it might be too deep. One of the things where CMOS is catching up with CCD is in the bit depth, where you read out like it's 12-bit sensor, 14-bit, or 16-bit. And that actually does make more of a difference than a lot of people realize in terms of the noise floors. So when you're trying to do short exposures, you really need a large bit depth, like the 16-bit sensor would work better than a 12-bit sensor. Because what happens is the very, very faint signal that you're trying to capture gets lumped in with the noise. Even if the signal is above the noise, when it gets digitized, if you only have 12 bits to digitize it, then the noise and the low faint signal end up in the same bin, and then you can't separate it. An analogy I try to use is like, imagine if all you had were $100 bills and nobody gave change. And if you bought a soda, it was $100 and you got no change. And if you bought a steak dinner, it was $100 and you got no change. Well, you'd run out of money pretty quickly that way. But if you had $1 bills, then you could buy a soda for $2 and you'd still have $98. So having that extra bit depth allows you to partition up the signal a lot more finer grained and separate down in the very, very faint area where you've got the read noise and the pattern noise intruding on the faint signal. You need to be able to tease that apart. If you don't have enough bit depth, you just simply can't do that. You can't calibrate it out. You can never recover that. It's called quantization error. If anybody wants a buzzword for that. Yeah. You probably know what I'm talking about.
Yeah. That's very interesting. Wow, Richard. This is good. Anything else?
I don't think so. You have anything else?
I can't think of anything. We covered a lot. This is very good, very informative. How can everybody get a hold of you?
I'm you can follow me on Twitter, Accidental Astro on Twitter and on Instagram.
Okay.
And my website is eveningshow.com.
Eveningshow.com. Okay.
Yep.
Fantastic. Well, I'll put links to both those in the show notes as well. Richard, I really want to thank you for coming on the podcast today. This is very informative.
Sure, Tim. Thank you very much for having me. Appreciate it. And
well, that'll do it for this episode of the Observer's Notebook podcast. I again want to thank Richard Wright for coming on and giving us a real great education on CCD and CMOS imagers. Hope you enjoyed it. We upload a new episode of the Observer's Notebook on the 1st and 15th of every month. You can subscribe to us on iTunes. If you do, please rate and review us. I really appreciate it. And you can now listen to us on iHeartRadio, SoundCloud, Spreaker, Google Play, and Stitcher, and, Amazon Echo. You can help support the podcast by donating to it via Patreon. You can give up to $35 a month, where you will receive 1 year's membership to the ALPO and producer credits on the podcast. And with that, I'd like to thank the producer of this podcast, Steve Siedentop, for his generous support of the Observer's Notebook. The link for Patreon, as well as the link for the ALPO, is in the show notes. You can contact me via email at commentman@commentman.net or on Twitter at ObserversNBpod. Until next time, my hope is that you always have clear and steady skies. Thanks for listening.